Linear relations, linear patterns. A pattern is said to be linear if there is constant additive growth. Constant meaning the same, consistent. We can see this kind of growth very clearly in tile patterns like the one in example 1. So over here in example 1, we see that our figure number is increasing by 1 each time. We're going from figure 0 to figure 1 to figure 2. And we can see that here, these 3 are the original 3 from figure 0, and they're right here in figure 1. And that means that the 2 that we've added are this one and this one. And now from figure 1 to figure 2, we have these 3 and these 2 that are right here, these 3 and these 2. So the 2 that we've added are this one up here and this one down here. So there's constant additive growth. Additive meaning adding the same amount each time. We can see that this pattern is linear because as we move from one figure to the next, the pattern grows by the same number each time. In this case, it's 2, the 2 there in red. Actually, let me make that red so that you can see where that is coming from. Example 2 is not linear. So let's look over at example 2. Here we start with these 3, which we can see are right here. So that means we've added, let's add in green here. We've added this one, and that one. So we've added 3 there. Now when we move from figure 1, here's 3, 2, 1, 3, 2, 1. So all these ones along the outside here are the ones that we've added. And what you should notice is that we add 3 there, but we add 4 here. So it's not constant additive growth. Moving from figure 0 to figure 1, the number of tiles increases by 3, but moving from figure 1 to figure 2, the number of tiles increases by 4. Actually, let me do that in green so that, again, you can see where that's coming from. This means that the tile pattern in example 2 does not have constant additive growth, adding by the same amount each time. We must have at least 3 figures to determine whether a pattern is linear or not. So supposing that we just had 2 figures, all we could see were those 2. Well, yeah, maybe we're going to add 3 next time, and they're going to go right here and there and there. And that would be constant linear growth. But when we see that we have a pattern of 3, we can see that it is growing by more each time. Similarly, here, maybe if we just saw those 2, here, this one and that one are growing. But maybe in figure 2, we added this one and this one and this one and that wouldn't be linear. So you need to have 3 figures to determine whether growth is linear or not. We always blank a tile pattern with blank. We always I can't even remember what I was thinking there. Let me think. We always blank a tile pattern with blank. We represent a figure number and number of tiles that in that figure using a shortcut. I know that. So this is shortcut. I'm going to pause for just a second. We always start a tile pattern with figure 0. So notice that in both of these tile patterns, it's figure 0 instead of figure 1. We always start with figure 0, and you may see why that is later, but for now, just know that we start with figure 0. We represent a figure number and the number of tiles in that figure using a shortcut. For example, in example 1, figure 0 has 3 tiles, and we represent it this way. Figure 0 has 3 tiles. Another way of reading that is f of 0 equals 3. Either way works. Figure 1 has 5 tiles. Figure 1 has 5 tiles. F of 1 equals 5. And figure 2 has 7 tiles. F of 2 equals 7. And so that we can see as our figure number increases by 1, the number of tiles increases by 2. When a pattern is linear, we can use what we know about it to determine the number of tiles in a given figure number and determine the figure number for a given number of tiles. In example 1, we can determine that figure 10 will have blank tiles. So let's see. I can see that figure 0 has 3, figure 1 has 1, figure 1 has 5, figure 2 has 7. So I can write up here, let's see. Figure 0 has 3, figure 1 has 5, figure 2 has 7. So let's see, how is this working? Well, I can see that if we take the figure number, here if we take the figure number and we add 3, we get it. Here we have to take the figure number and multiply it by 2 and then add 3 to get the number of tiles. If we take the figure number 2, multiply by 2 and add 3, we get the number of tiles. So it looks like we're taking the figure number, multiplying it by 2 and adding 3. So figure 10, we take that, we multiply it by 2, that'll be 20, and then add 3, that will be 23. So we would say f of 10 equals 23. And the figure number that will have 35 tiles is figure, so let's see. Which figure number will have 35 tiles? If we take 35 and we subtract 3, that's 32. And then divide by 2, 32 divided by 2 is 16. So figure 16 will have 35 tiles. All right, determine whether each tile pattern is linear or not. Okay, so what I see here is that in figure 0, we have this one right here, and then 1, 2, 3, 4, 5, 6. This one right here, and then 1, 2, 3, 4, 5, 6. So it looks like we're adding these 6 on. So I'm going to color those in. And then the other thing I can do is I can say figure 0 has 7, because 1, 2, 3, 4, 5, 6, 7. And I can say figure 1 has the 7 plus the 6 is 13. So these are all the tiles that were in figure 1. So we're adding these ones in figure 2. So it looks like we're adding these 6. So for figure 2 has the 13 plus the 6, which is 19. So I can see that as we are increasing our figure number by 1, here we are adding 6. Here we're adding 6. And so that is a So we're adding 6 and adding 6. So that is linear. It's a constant additive growth. Over here, we start out with 1, and then it looks like we add these 2. So we add 2. And then here are the 3 right there. And then we add those 2. So that also appears to be linear. So figure 0 has 1, figure 1 has 3, figure 2 has 5. So that is also linear. And that is the first video for linear relations, and it's on linear patterns.